MBA633 instructional video prepared by Professor Amit Tata, School of Management, George Mason University. In this segment, we'll introduce some basic terms and concepts of sampling, based some terminology and some concepts. Once we have these squared away, then in a later segment, we will actually see what are the mechanics of drawing inferences using sampling. So let's start with some of the terminology and concepts. The first term that we'll introduce is population, and you can see on the right hand side I've drawn a big shape with the word population next to it and the letter capital N. So what is a population? A population is simply a collection of so-called units of interest, and I'm generally interested in some property of the population. One example of a population could be the collection of all registered vehicles in the state of Virginia. Okay. Another example of a population is likely voters in the 2012 presidential elections. So in the first case, the units are the registered vehicles. In the second case, the units are the likely voters. So there are many different properties that one could be interested in for each of these populations. Let's take a couple of examples. For example, for the registered vehicles in Virginia, I might be interested in the average amount spent per year for repair on each of these vehicles. So I'm representing that by the letter mu. So mu would represent the average amount spent per year per vehicle for repair. I might also be interested in the standard deviation of the repair cost per vehicle per year, and other properties of the population as well. These are just two examples. I'm picking these two because they happen to be two of the most common properties of population that one tends to be interested in. For the second population, say likely voters in 2012, a property of that population that we might be interested in is what proportion of these likely voters would vote for candidate Romney, for example. I'm representing that by the letter P. So these three properties that I've just illustrated, cited as examples, mu, sigma, and P, these are what are called population parameters. So in other words, population parameters are simply properties of a population that we're interested in estimating. Okay. Now, for a variety of reasons, usually for lack of cost, lack of money and or time, it's either impossible or undesirable to analyze every unit in the population or measure every unit in the population. Either it would take too much time or too much money to do so. For example, I couldn't call up every registered vehicle owner and ask them how much they spent on repair. I couldn't possibly talk to all likely voters in a reasonable amount of time. So failing not having the ability to analyze every unit in the population, what we do is we pick a sample. A sample is simply a subset of the population. That's why the size of the sample is represented by small n, whereas the size of the population is represented by capital N. So a sample is simply a subset of the population. Now the subset has to be chosen in a particular way. Okay, and one common way to pick a sample from a population is what's called random sampling. In random sampling, every member of the every member of the population has equal likelihood of being picked into the sample. Okay. Now, random sampling has its own advantages and disadvantages. There are other methods of sampling called stratified sampling and so forth. We will not be getting into techniques of sampling, but remember, one essential property of a sample is that it somehow should be representative of the population. That one word is easy to say, but it's pretty difficult to execute in practice. So a sample should be representative of the population. So once we get a sample, what do we do with it? We measure the units in the sample and try to guess what the population parameter would be from that. For instance, if I want to estimate what the population mean might be, I would measure the sample mean. And do you see I'm using a different symbol to represent it? It's x bar. If I want to estimate the population's standard deviation, I would estimate the sample standard deviation. And if I want to estimate, if I want to know the proportion of likely voters who might vote for candidate Romney, then I would measure the sample proportion. In other words, let's say I picked 100 likely voters as my sample. I would ask each of them, would you vote for candidate Romney? Each person would say yes or no, and based on that I would get a proportion from the sample. These measurements that I do on the sample are what are called sample statistics. Okay, so the basic process that one goes through when one uses sampling is to use sample statistics to infer population parameters. Okay, so we use sample statistics to make inferences about population parameters. Now, once having realized that, there is another important distinction to understand, and that is that the population parameters mu, sigma and p, these are constants. In other words, if I had enough time or money, I could compute those three things exactly with absolutely no uncertainty. Okay, it's just that I do not have the resources, or it's physically not possible to do those measurements, and instead I have done my sample measurements and I have the sample statistics. Now, unlike the population parameters, the sample statistics are random variables. There is uncertainty associated with them. Why? Because in picking a subset from the population, I am subject to the vagaries of sampling. I can never be absolutely sure of the elements of the units that I'm getting in the sample. So every time if I were to pick different samples from the same population, I would get slightly different values of each of these sample statistics. So for example, if I picked a set of 100 likely voters and computed the sample proportion once, if I pick another set of 100 likely voters, even though they're representative, I might get a slightly different value of the sample proportion. Okay, so the main thing, conceptual distinction to remember, is that sample statistics are random variables. There's uncertainty associated with them. I'm never quite sure exactly what I'm going to get. I anticipate that they will be somewhat close to the population parameters that they're trying to estimate, but they will be slightly off. And the uncertainty is how much off are they likely to be. So population parameters are constants, just that they're unknown. The sample statistics are known, we do our measurements, but they're uncertain. Now you know that anything that's a random variable, so the sample mean, the sample standard deviation, and the sample proportion, these are all random variables. Any random variable has a distribution. Okay, so the distribution of a sample statistic is what is called a sampling distribution. Hence we have a sampling distribution for the sample mean, we have a sampling distribution for the sample proportion, and as you will see later, we will have a sampling distribution of the sample variance, not of the standard deviation, but of the sample variance, but you know that the two are related. So essentially what we are saying is, if you take any one of the sample statistics, say for example the sample mean, it will have a distribution. In other words, there is a pattern of uncertainty, and I think you can guess by now what that pattern might look like. I would expect it to be close to the population mean. I don't know what the population mean, but I expect the sample mean to be something close to it. I don't expect it to stray too far. So I would be expecting a distribution which is somewhat bell-shaped perhaps. And later on you will see if the sample is large enough, in fact that's what it is. But my intuition tells me that the sample mean should be bunched around the population mean that I'm trying to estimate. I'll be very surprised. Only very rarely should it stray a lot from what I'm trying to measure. There's a chance that could happen, but the chance is low. The other thing that you can read between the lines here is that if I want to reduce my uncertainty in estimating the population parameter based on a sample statistic, I really need to get as big a sample as I can. So the larger the sample, the lower the uncertainty. I think intuitively you can see why that would make sense, that this sampling distribution would get skinnier. Okay, so to summarize, what we're doing in sampling is picking a subset of a population and doing measurements on the sample. The measurements on the sample yield what are called sample statistics, and based on the sample statistics we try to infer the corresponding population parameters. Now, the population parameters are constant, but the sample statistics are random variables. And every random variable has a distribution, in other words, a pattern of uncertainty. So the pattern of uncertainty of every sample statistic is called its associated sampling distribution. So you have a sampling distribution of the sample mean, a sampling distribution of the sample proportion, and a sampling distribution of the sample variance. And in subsequent segments, we will see what these distributions look like, and based on those distributions, how one can make inferences about the population parameter based on sample statistics. Okay, so in the next few video clips, we will be getting into the topic of inferencing, which is the mechanics of inferring population parameters based on sample statistics using the concept of sampling. Okay.